Okay, so let's get started. Hello, everyone. Thanks for joining us today. My name is Babak Sirajeh from Indiana University, and I'll be your host and moderator today. So this is our third presentation in the long-range colloquium that is organized by the Virtual Science Forum. A quick introduction, if this is your first time joining us, the Virtual Science Forum is an open, collaborative, and volunteer-run initiative to facilitate online scientific seminars and meetings. If you would like to help this effort by joining our group or organizing a session or suggesting speakers, please visit our webpage where you can find information and resources about how to do that. Also, all of our content is available on GitHub, and on the video recordings are available on our YouTube channel. So I'm going to provide some links to these pages. Also, our next colloquium will be on May 27th. It's going to be given by Nicole Spalding of ETH Zurich. I want to also just thank the institutional support that has made this possible, in particular by the Delft University of Technology and Indiana University Bloomington. So a quick note on the Q&A. So there is a button, there's an option to raise your hand that you can find in the participant panel that is at the bottom of your screen. I'll be moderating that panel, and we'll let the speaker know that there's a question, and then you can ask a question live. You probably need to unmute yourself first. Okay, so let's move. Actually, let me share this message, the links to everyone that I promised. Okay, here you go. So let's move to our colloquium today, which is presented by Vidya Madhavan of University of Illinois, Urbana-Champaign. She will tell us about microscopic evidence for chiral superconducting order parameter in the heavy fermion superconductor uranium telluride. Vidya?
Very good. All right. Thank you very much for inviting me to do this. I'm very happy to be doing this, especially since I haven't traveled anywhere or given any talks for a long time. I just wanted to say these are very strange times indeed, and I appreciate all of you joining us, and also I hope you're all doing well. Welcome. Today I'm going to talk about scanning tunneling microscopy measurements of the newly discovered superconductor uranium ditelluride. I want to tell you that I don't know if my voice is going to remain constant or if I'm going to start fading. If I do start fading, please let me know immediately. I cannot see the chat, but Babak will unmute himself, or you could unmute yourself and tell me to speak louder. If something is horribly unclear, please feel free to stop me. Otherwise, we can always have questions at the end. Okay, so let me start. So the crystals that we worked on were all grown by Sheng Ran from NIST, was a postdoc with Nicholas Butch. And in fact, these are just beautiful, gorgeous crystals. And we know by measuring them that they're all in one phase. And none of these measurements would have been possible without these very nice crystals. The STM work was sort of driven by my postdoc, Lin Zhao, with the help of graduate students Sean Howard, Zhenyu Wang, George Rodriguez, and Anuva Aishwarya. We had a lot of theory support. In fact, a lot of the stuff that I'm about to show you has been very difficult to understand. You'll see towards the end of the talk. I'll show you things that we actually still don't understand. But we wouldn't have understood even what we did without the theory support of Ziqiang Wang at Boston College, Manfred Siegrist at ETH, and more recently, Barry Bradlin at UIUC. Okay, so let me just move this. It's blocking me. Great. you know, over the last 15 or 20 years since the discovery of topological insulators, you know that we've been searching quite intensely for two-dimensional materials with edge states. In fact, we've been searching for topological materials with edge states. Now, normally, even in a normal material, you might have ordinary edge states. But the thing about these ordinary edge states is that they're not protected against backscattering. So instead, if you have a topological material like a quantum spin Hall system, then you expect to have helical edge states. These helical edge states are protected against backscattering by normal impurities. However, they're still not robust against backscattering by magnetic impurities, which could take an electron from one spin channel to another spin channel. So the search has been on for quantum anomalous Hall systems, which are magnetic systems where you expect to see these chiral edge states. And here, backscattering is completely forbidden. And in fact, if you had a quantum anomalous Hall insulator at room temperature, you can expect that you'll have these dissipationless edge modes, which might be extremely useful for devices. So this is just ordinary topological materials that are very interesting for a variety of reasons, including the possibility of realizing these edge states. However, we also know, oops, I did something, okay, that there is a possibility of having superconductors that are non-trivial. That is, now I'm talking about topological superconductors. Just like ordinary insulators cannot be adiabatically transformed into a topological insulator without closing and opening the insulating gap, similarly, topological superconductors cannot be adiabatically deformed into a regular superconductor without opening and closing a gap. So these are actually a distinct phase of matter. And in these topological superconductors, one of the interesting things is that depending upon the topology of the bulk, you also expect to see very interesting both chiral or helical edge and surface states. And of course, the important thing about these superconductors is that they are a fundamentally new phase of matter. Now, the first question one might ask is, where might you find such topological superconductors? And the answer is, one of the places to search for these kinds of non-trivial superconductors is in triplet p-wave systems. So just a quick reminder, you know, normally we expect a singlet pairing in conventional superconductors where pairs are composed of electrons of opposite spin. Is someone saying something? Sorry, okay.
You can go ahead, sorry.
Okay, all right. And these Cooper pairs, because of obvious fermionic symmetries, they must have an orbital angular momentum of either S or D, etc. But you obviously can imagine situations where you can have Cooper pairs with the same spin, that is same spin pairing. These are the triplet states. And when you have spin-triplet pairing, then by the symmetry constraints tell you that the orbital momentum must be P or F or so on. So it's these triplet superconductors where we expect to find unconventional topological superconductivity. And in fact, you can easily show why these edge states in these triplet superconductors might look like Majorana modes. So let's just ask the question, what do you expect for a Majorana particle? So here's the Majorana condition that the creation operator of a particle should be the same as the annihilation operator. So if you want to achieve this, one natural place to achieve Majorana fermions would be to use a superconductor which naturally has particle-hole symmetry. Now, the excitations of a superconductor are Bogoliubov quasiparticles, which are superpositions of electrons and holes. So here's a creation operator and an annihilation operator. If you want these Bogoliubov quasiparticles to mimic Majorana fermions, you want to set these two to be the same, to be equal. Now you can see immediately when you set this to be equal to this, you require the UKs and VKs, the magnitudes of these to be the same, and perhaps this is easy to achieve. But the big problem we have is that even if you do that, the spins of the creation operators are flipped. So in a normal singlet superconductor, where you have opposite spin pairing, you can't easily realize Majorana fermions without having to do some extra work. However, in a triplet superconductor, spin is eliminated as a separate degree of freedom. And so you can naturally see that Majorana particles can be natural, triplet superconductors might be natural platforms to realize Majorana edge modes. So in any case, triplet superconductors could be topologically non-trivial. It all depends on details, but some of them could be topologically non-trivial. And if they are topologically non-trivial, then you expect to see either chiral or helical Majorana, propagating Majorana modes at the edges of these samples. So the question is, what kinds of materials do we have so far which are candidate triplet superconductors? And we have very few. So we had strontium ruthenate, but the jury is still out on that because new experiments show that perhaps it's not a simple chiral p-wave superconductor. It might be more complicated. Uranium platinum-3 is one example, and there are very, very few examples of such systems. So a natural place to look for triplet pairing is in the vicinity of ferromagnetic fluctuations. So a lot of work was done in the late 70s and 80s, early 80s, where theorists showed that if you have strong ferromagnetic fluctuations, then in the vicinity of these fluctuations, if you have superconductivity, then triplet pairing is natural in these circumstances. So uranium-based compounds, many of them have both superconductivity as well as ferromagnetism. And so they're also natural places to look for triplet superconductivity. And in fact, uranium tellurium-2 is especially nice because it doesn't have ferromagnetic order. And yet we expect it to have ferromagnetic fluctuations. So perhaps if superconductivity were found in uranium tellurium-2, there's a chance that it might be triplet. So about in 2018, Sheng Ran, Nicholas Butch, and others found that uranium tellurium-2 is a superconductor. That was the first time it was discovered to be superconducting. And very quickly afterwards, there's been a host of papers showing many, many intriguing properties. So let me just show you the first important thing. This was in their first paper. This is a measurement of the NMR night shift. And and here's TC. TC for these materials is 1.6 Kelvin or so. So if you look at the night shift as you go across TC, it shows very little change. Recent measurements actually show that there's a tiny change of the night shift as you go across TC, but even that change is much smaller than what you would expect for a singlet superconductor or a D-wave superconductor. So this unchanging night shift is a strong indication that there is triplet pairing in this system. This is specific heat measurements. So you can see the large specific heat jump right at TC. This is particularly large. And this indicates, and I'll show you, the normal state of this material is also very interesting. This large jump indicates that a heavy band is involved in pairing. But the more intriguing thing is that if you look at close to zero temperatures, what you see is a large residual specific heat. And this large residual specific heat might indicate, we don't know, it might indicate that there's a sort of a sea of unpaired electrons that still exists below TC in this system.
So Vidya, we have a question. Anton?
Yeah, sorry, can you please refresh my memory a bit? Can you remind what is the relation between the night shift and the type of the superconductivity?
Yes. So night shift. So you have if you turn on, so if when you measure the night shift, if you have singlet pairing, right? As you go through TC, you should see a change in the night shift, right? And the change is quite dramatic as it goes through TC. So for triplet pairing, the reason that there's no change in night shift is because if you have a triplet pairs, they're already in a sort of a ferromagnetic state, and a magnetic field doesn't actually do anything to these triplet pairs. So your night shift doesn't change as you go through TC. Does that make sense?
Yeah,
So
okay.
magnetic, right, yeah.
Doesn't that also depend on the sort of triplet pairing? So
so there are many details here. For example, one thing that I have to mention here is that this was done in only one direction. You can ask, does the night shift show no shift in other directions as well? Because, so there are lots of details. And so also the exact form of the night shift, temperature dependence does depend on the details of the pairing. But this very flat night shift across TC is a strong indication of triplet pairing. At least it's a first indication of triplet pairing.
Yeah, all right, got it, thanks.
Okay. So there are other interesting and intriguing observations. One is that under pressure, although superconductivity seems to be suppressed, there's an emergence of another superconducting order parameter. Moreover, there's also evidence for magnetic order. So at zero pressure, you have no ferromagnetism, but at high pressures, it seems like there might be some magnetic order. The magnetic field behavior is also very interesting because the HC2 is extremely high. It's about 15 Tesla, depending upon the direction. So the maximum is 15 Tesla. There's more than one reentrant superconducting phase. In fact, at very high magnetic fields, actually this happens only in certain directions. This is, theta is the direction, right? Theta and phi. But in certain directions, in high magnetic fields, you have another superconducting phase. So all of these, if you take all of these together, it indicates a very unconventional superconductor. And it also indicates that this actually might be triplet pairing. You know, the magnetic field, the reentrant superconductivity is often a sign of triplet pairing. So since the material was discovered to be superconducting in 2018, there have been a ton of publications. This is very short list. Actually, I did this 5 months ago. There are many more. So it's an active and growing area of research. So our goal was to study this material with scanning tunneling microscopy. So let me just spend a couple of minutes describing STM. So
Vidya, there are a couple other questions, maybe. Joshua? Yep.
Yes. So how would the night shift and specific heat compare for, say, uranium germanium 2? How would it differ?
Uranium germanium 2 is not superconducting without pressure.
Mm-hmm.
So you need to pressurize it to make it superconducting. If you're asking about this residual specific heat, this is not normal. You expect this, if in a superconducting phase, if all the electrons are paired, then this should go to 0. Now, sometimes I know that in some materials when, initially for strontium luthenate, for example, I think we did see sort of a residual specific heat signature. But then that was much smaller. Also, one thing to realize here is this number is half the normal value. So this is not something that you would normally see in a superconductor. For uranium germanium 2, I don't know anything about the night shift. Yeah. So there are materials that are, that are expected to have triplet pairing either under pressure or in magnetic fields, or but I think there are uranium tellurium ditelluride and uranium platinum are the two materials that at ambient conditions are thought to be triplet superconductors, and perhaps strontium luthenate.
Thank you.
We have a second question by Sentil.
Yeah. Hey, Vidya. So this specific heat curve, it seems like compared to the normal state, it's not doesn't conserve the entropy.
Yeah. So yeah. So I mean, this is. You should talk to John Pierre Paglioni about this, or Nick Butch. They have some ways of explaining this lack of entropy conservation. I don't know exactly how they explain this, but you're right. It does seem to not conserve entropy. There's also, I have to say, this is not raw data. They've made some background subtractions. So yeah, sorry, Sentil, I don't know the exact answer. But there is, I think, in the paper, if you read the paper, they do explain what might be going on. Okay.
Okay, thanks.
Okay. So yeah, we do STM. STM is a very, very simple instrument. So you bring a very sharp metallic tip in close proximity to the sample that you want to study without touching, so a few angstroms away. You apply a tiny bias between the tip and the sample in millivolts, and electrons tunnel from the tip to the sample or sample to the tip, and we measure the tunnel current, and that's what we do. We measure this tunnel current as a function of position in the XY along the sample in the XY plane. We also measure the tunnel current as a function of bias voltage and so on. So it's a very simple measurement. A lot of our STMs operate at low temperatures in ultra high vacuum, mainly for sample cleanliness reasons, as well as liquid helium temperatures are lower. That gives us better energy resolution. Our energy resolution is actually determined by the temperature. A very nice way of visualizing a scanning tunneling microscope experiment is to do the following. You can think of the sample and the tip as just two reservoirs filled up to the Fermi energy with electrons. When you apply a potential difference between the two, you raise the Fermi energy of one with respect to the other. And initially, when there's no bias voltage applied and they're in close proximity, the Fermi energies line up. And you cannot have tunneling because there are no, this fill states here, electrons cannot tunnel from one to the other. Now, when you lift the Fermi energy of one with respect to the other, electrons can now tunnel from the fill states of the sample in this example to the empty states of the tip. And you can see pictorially that the tunnel current must be proportional to the integrated density of states from the Fermi energy to the bias voltage. And in fact, that's what it is. So the tunnel current is proportional to the integrated density of states. But in STM, there is an additional interesting feature, which is that each state is weighted by the square of the wave function. And in fact, the square of the wave function is really important when we do measurements like quasi-particle interference. And it also gives us information on the charge density waves and so on. But in the stuff that I'm going to show you today, this is not going to be important. Because the tunnel current is proportional to this quantity, you can show very easily that the current, it dies exponentially into space as a function of height. And so we can just measure the tunnel current as a function of position to obtain information on the topography. And the second kind of measurement we make is, since I is proportional to integrated density of states, we can measure di dB and plot that as a function of bias voltage, and that just is proportional to the local density of states. So this is just an example of what an STM might look like. In fact, we have 4 scanning tunneling microscopes in my group. The one that was used to do all this work is actually a commercial system from Unisoku. It goes down to 300 millikelvin and it has 11 Tesla magnet. Okay, so uranium tellurium 2. Let me just start with the crystal structure because that's really important to understand the topography, as well as in case you wanted to work on the system, it might be important for you. It's an orthorhombic crystal structure. And this is the unit cell that you see here. These red dots, these red balls are actually uranium. And each uranium atom is surrounded by these tellurium atoms in a prism kind of configuration. You can see it better here. That's why I have this. So we typically, what we do to study samples by STM is we glue a rod to the sample and we sort of cleave it, meaning we hit the rod in ultra high vacuum and the sample cleaves. In fact, it's not at all obvious that this kind of crystal structure should cleave. But very fortunately for us, it cleaves and it gives us these beautiful surfaces. If you look carefully at one of these surfaces, what you see is chains of atoms. So here you see much more clearly, you have one chain of atoms and then you have another chain of atoms right next to it, which is slightly dimmer. So you have these chains of atoms, and these chains of atoms are in fact tellurium atoms. So you can ask by looking at this surface, what is our cleave plane? And in fact, our cleave plane is not parallel to these nice crystal directions, but it's in fact this direction. And this direction is parallel to the 011 plane of this crystal. Okay, and how do we know that this is the cleave plane? In fact, there are many reasons we know this. So let's just look at this 011 plane from the top. This is the top view of the 011 plane. What you see is you see these rows of tellurium atoms. In between are the uranium atoms, but if you look carefully right here, you can see that the uranium atom is slightly lower. And in fact, even the green tellurium atoms and the white tellurium atoms are not in the same level. One is lower than the other. So what we see in STM is these rows of tellurium atoms, and we don't really see the uranium atoms, okay? And we have other evidence that this is our cleave plane. So this is the view of the crystal in a layer by layer configuration in the same direction as our cleave plane. If we have this kind of layer by layer configuration, then you can see that if we had any steps in the STM, then the step height should be 5.6 angstroms. Also, like I showed you earlier, this is the top view. Twice the distance between the tellurium rows is 15.3 angstroms. So you look at our step heights and it's 5.5 angstroms, and twice the distance is 15.5 angstroms. And so everything matches, and we're 100% sure actually that this is our cleave plane. This is important because when you look at ARPA's data, I just want to warn you that some of the ARPA's data, they take a lot of trouble not to cleave along this plane. And so the ARPA's data is shown along on a completely different face. Okay. So now the first thing I'd like to do is talk about the normal phase, because normal state of this material is extremely interesting. It's actually a heavy fermion metal. And you can see this both in the measurements of magnetization as well as the resistivity. So the resistivity measurements, they show, it's a metal, but resistivity shows an increasing resistance with decreasing temperature. And that is because the localized moments are interacting strongly with the conduction electrons. And that gives rise to an extra scattering channel whose scattering strength actually increases with decreasing temperature. And that's this increase that you see here. So this tells you that this is sort of like a, like a Kondo system, a heavy fermion system. The other thing you can see is in the magnetization along the B-axis, you can see the magnetization actually decreases and then saturates at low temperatures. And this is very typical for a Kondo system. And this decrease in saturation is because the localized moments in the systems have been actually screened by the conduction electrons. And once they're screened, they no longer behave like spin-full objects. Okay.
There's another question, Vidya.
Yes.
I think by Anton.
Yeah. So I understand that this sounds likely that localized moments would freeze out and interact stronger at low temperatures. But is there direct probe of that, or is this an assumption?
No. So there are many ways of looking at this. I'll show you STM data where we see a resonance right at the Fermi energy. So that's one direct way of probing this.
Yeah. Okay.
So, but remember, this material has been shown not to have ferromagnetism. So there's no ferromagnetic order. So that's another indication that something strange might be happening, right? So you have moments, but they're not ordering. So then there's a competition between ordering and the Kondo effect, which
right.
So I'll show you data in a second, but the fact that it's a heavy fermion system is really interesting. Just to remind you, you can have this so-called Kondo effect where you have a single magnetic impurity in a metal. And in that case, something very beautiful happens. The conduction electrons of the metal interact with this localized magnetic moment. The interaction strength grows as the temperature is decreased. And at some low temperature, you make a single state where the localized moment is completely screened by the conduction electrons, right? So that's the Kondo effect, the single impurity Kondo effect. Now, if you have a bunch of localized moments on a lattice, and you have also have conduction electrons, you have something similar happening, but this is, of course, your typical heavy fermion system. Here again, you have interactions between these localized moments and the conduction electrons, and at low temperatures, you can screen these localized moments and you can get something very similar happening. The important thing here is that in this heavy fermion system, what you expect is that below the Kondo coherence temperature, you should see the development of a very narrow F band close to the Fermi energy and with a huge effective mass. And the interesting thing in this system is that when it turns superconducting, you expect this heavy band to be participating in superconductivity. So this is a DI/dV measurement. This is at 300 millikelvin, but this is over a pretty large energy scale. And what you see here is this strange feature. 0 for us is the Fermi energy, by the way, of the sample. So you see this strange feature right at the Fermi energy. And the question is, what is this feature? And in fact, we know exactly what this is. This feature is due to a phenomenon called Fano resonance. So what happens normally is that here you have a tip and you have a sample. And let's say you have a narrow density of states, a sharp density of states right at the Fermi energy in your sample. Typically, when electrons tunnel from the tip into this resonance, if the tunneling process is strong enough, all you would see in your density of states is a sharp peak in the density of states. But often you have other co-tunneling processes where the electron at the same time can perhaps tunnel into the conduction band. And in that case, if you have a situation where for maybe matrix elements reasons or something like that, the tunneling into this resonance is not very strong. And tunneling into the conduction electrons is in fact as strong or stronger, then what you see at the Fermi energy is, instead of this sharp Lorentzian resonance, you would see a funny line shape, which is called a Fano line shape. Fano gave an explanation for these line shapes in optical spectroscopy, where it's the same process, where you have an interference between two tunneling paths, one going into a localized resonance and one going into the conduction states, electron states. So whenever you have this interference process, you get this Fano line shape. And that's exactly what we see in these materials. One of the first examples of this Fano line shape in STM spectroscopy was STM measurements on individual cobalt atoms that were deposited on the surface of gold. And this is actually a Kondo system. So at low temperatures, you should see a Kondo resonance, which should be a sharp peak in the density of states. And instead, you see this Fano line shape. And that's exactly due to this process. So it's just a line shape. But it's interesting because once you know what this is, you can actually fit the spectrum and get the width of the resonance, right? Okay, so such line shapes have been seen in other heavy fermion systems as well. I just wanted to mention that. And so this is a Kondo resonance, or the heavy band at the Fermi energy. That's what this is. And we can fit this quite simply using the Fano formula. From this, you get the Kondo coherence temperature to be about 30 Kelvin. You get a width of this band of a few millivolts, like around 4 millivolts, right? So it's a pretty narrow band. And the position is centered very close to the Fermi energy. So it's about a millivolt from the Fermi energy. So you have a narrow band right at the Fermi energy, and this is your F band. This coherent temperature of 30 Kelvin is also very consistent with the magnetization measurements. Along the B-axis, you can see this downturn, and that's when the Kondo coherence kicks in. Okay, so now let's zoom in. Just looking at the time. Let's zoom in to low energies, where we expect to see the superconducting gap. And so remember, this was a very large range spectrum. This is plus minus 40 millivolts. Now let's zoom in to 1 millivolt. And when you zoom into plus minus 1 millivolt, what you see is a small dip, right, centered at the Fermi energy. And this dip, I'm claiming, is the superconducting gap. In fact, this is a series of spectra taken along a line on this sample. So, so you can see with your eye, there's no coherence peaks. This dip is very shallow. And in fact, this dip is extremely shallow. Let me just show you that. So here is, for example, with the same system, with our system, we obtained data on MOTESE, which is also an interesting superconductor with a similar TC. And you can see that that superconductor, that's the spectrum, and you can see quite a nice spectrum with coherence peaks, and the density of states not quite going to 0, but pretty deep, okay? So compared to this, the red spectrum is the superconducting spectrum on uranium ditelluride. So it's extremely shallow.
So Vidya, I have a question. What is the temperature for these? What temperature are these done at?
300 millikelvin.
Okay, that's the lowest temperature. Okay.
Yes. So this gap does disappear in a magnetic field. So that's indicative. I mean, that suggests that it's a superconducting gap. But we also did one thing which is really important. What we did was we took a sample and we did Laue specific heat and STM measurements on the same sample, right? And so the Laue measurements tell us that the whole sample is in one phase, which is really nice. So this is not due to some strange phase. The specific heat measurements tell us that this sample is superconducting, and in fact, the TC is around 1.6 Kelvin. And our STM measurements, we see the shallow gap, but the shallow gap disappears right around TC. So if you take all of this together, you have to, you have to sort of believe that this shallow gap is the superconducting gap. Okay, so just a couple of things before I talk more about superconductivity. One is that we found something quite interesting. We found that the Kondo resonance shows variations in real space over atomic length scales. And so does the superconducting gap. And these two are anti-correlated. So for example, this is a bunch of spectra taken from point A to point E, right? This is within one unit cell. And you can see the Kondo resonance, the height changes. It's highest at A and lowest at E. However, the superconducting gap does the opposite. It's most shallow, and in fact, it's actually smaller at A, and it's deeper and broader at E. So the Kondo, this sharp resonance at the Fermi energy is sort of anti-correlated with the superconducting gap. We don't understand why this is. The Kondo, you know, this feature, there's resonance varying over atomic length scales, has actually been seen in other heavy fermion systems by different groups. This is Seamus and Ali Azdani, both working on uranium, ruthenium, silicon. And here you can see that the Kondo effect varies, all of the parts of it, Q, gamma, everything changes over atomic length scales. So this can be attributed perhaps to orbital effects, meaning that as you go from position to position, how the tip couples to the localized orbitals might be changing, and that might give you these changes. But we still cannot explain why the superconducting gap varies inside a unit cell. So this we still do not understand. Okay, so this is the system. We have quantum criticality, meaning a strong quantum critical ferromagnetic fluctuations. I haven't shown you data for that. You know, you can read the literature, but it's pretty clear that there's ferromagnetic fluctuations. There's a heavy band close to the Fermi energy, so it's a heavy fermion system. It's superconducting. The night shift measurements suggest that it's triplet pairing. And then the question would be, is it a chiral triplet superconductor? In which case it might be topologically non-trivial. So it might be a topological superconductor. So that's one of the questions.
Vidya, we have another question, although I don't see the raised hand anymore. Okay, Victoria.
Yeah, I just wanted to tell about the previous slide regarding the superconducting gap. I mean, my understanding is that superconductivity is like a many body effect. So if you speak about like superconducting condensate or stuff, you have to have many electrons for that. If you change the positioning of the tip depending on the atomic structure, then you have like several electrons around, or roughly speaking, certainly it's like if it is like a metal, there is a gas of electrons and a liquid. So I'm not sure one should call this a superconducting gap. Maybe it's a result of the tunneling current for this position or for that position, but I'm not sure that should be called a superconducting gap, and that might be the answer for your problem.
Well, okay, I understand what you're saying. I would still call it a superconducting gap, but I agree with you that we have matrix element effects. So what we are measuring is not simply, you might say, okay, there might be matrix element effects that give you a certain shape for the superconducting gap that might give you this change from position to position. One thing is that this is the superconducting gap, or at least should be the superconducting gap because of two reasons. It does disappear at TC, and it does disappear at HC2 for this sample. So it's sensitive to magnetic field and it's sensitive to temperature. So I would say that this feature here represents, okay, I think this is a better word for it. This feature here represents the superconducting gap with some matrix element effects probably, which might be causing this kind of spatial variation. That's entirely possible. We don't know yet, yes.
Okay, fine.
So we have a few more questions. Let's see. Maybe Akash, you can ask.
Yeah, okay. Thank you. Earlier you said that because of Kondo effect, the spin moments get screened out. At the same time, you need spin fluctuations to mediate superconductivity. So does this screening out mean that the underlying spin fluctuation mediated interaction is also getting weaker at lower temperatures or not?
No, in fact, this material has very strong spin fluctuations at low temperatures. So when you screen out the localized moments, it doesn't mean that the spin fluctuations are also getting quenched. I don't think that's necessary, because so spin fluctuations have to do with spin-spin interactions, right? Is that what you're saying? So if
Right, yeah.
screening of the localized moments, perhaps the fluctuations are dampened, but just experimentally, that doesn't seem to be the case. Even though you don't have, it's true that when you have a screening process of this kind, then you don't have magnetic order. That's true. But
right.
experimentally, they found that there's strong ferromagnetic fluctuations even at low temperatures. So that's just an experimental observation.
Thank you.
Okay. Just question about timing. How much is left, do you think? Because I want to manage the questions. Or how much more time do you need, you think?
I think I'm supposed to finish in what, 10 minutes, but I think I'll need about 15, maybe 15 minutes.
Okay. So that's good. So let's have one more question. Maybe this is the time. Yeah. Somesh?
Hi, Vidya. So I wanted to ask you about, so do you have any calculation via DFT for the band structure? So just to understand what band is responsible for the superconductivity?
Yeah, so there are calculations. I have a slide at the end. Let me just show you. There are multiple people. I mean, I don't have all the groups here, so forgive me if I haven't picked up someone's calculations, but here's one, for example. So this is the Fermi surface. Here are some of the bands right near the Fermi energy. I would say that this is still the beginning stages, and we don't have a full grasp of the band structure yet. There are heavy bands near the Fermi energy. There's more than one band near the Fermi energy, but that's all I can tell you. And this is approximately what the Fermi surface looks like. And RPLES data shows something that looks like this. Now, how much of these bands are tellurium bands, how much of this band is a D band, and how much of it is F. So there are 3 bands in this material. There's P, D, and F. And how much of this Fermi surface comes from those 3 orbitals, I cannot tell you.
All right. Thank you.
Sure. Okay. So yeah, so it's an interesting material. We have a lot of open questions. The question is it chiral? Is there broken time reversal symmetry? There have been suggestions of non-unitary pairing, and I don't want to get into this right now, but essentially this would imply that half the electrons are not paired, which would easily explain the specific heat, residual specific heat. But for any of these proposals, one has to be careful. One has to sort of take a look at not only the crystal symmetries, but also, is spin-orbit coupling important or not, and so on. So there are many open questions. So let me just spend the rest of my time, maybe 15 minutes, asking what other information can we get from STM measurements and trying to answer that question. And also I want to show you a few mysteries. So we studied the sample for a long time, and there are some things we understand, but there are a few things quite important things that we do not understand. And my feeling is that if we were to actually have a theory and we were to understand what is actually going on, we might be able to, get a deeper understanding of the order parameter of the system. And you'll see what I'm talking about in a few minutes. Okay. So one of the things that you have in a superconductor is you have Andreev scattering processes. And many of you are familiar with these processes. If you have a normal area in proximity to a superconductor, then electrons in the normal metal can scatter off of the superconductor in a very interesting way, where the electron coming in goes into the superconductor as a Cooper pair, while simultaneously retro-reflecting a hole. So this kind of process is called an Andreev process. And the interesting thing about these Andreev processes is that when you have regions in a superconductor, like close to an edge, which are normal, these kinds of areas, you might actually have bound states called Andreev bound states. And these bound states occur when the electrons in the normal metal can actually scatter and constructively interfere with one another. So the phase of this electron that's scattering from one side to the other side, if it can constructively interfere, then right here in this normal region, you can have an Andreev bound state. So the phase actually is quite simple. You can write a very simple expression for the phase, and you can show that depending upon what the superconducting order parameter is, different edges in the superconductor can give you different kinds of Andreev bound states, right? So one way to understand this Andreev bound state is just like the Bohr-Sommerfeld quantization condition. You have constructive interference if the phase condition is satisfied. So just to give you an example, if you have a D-wave superconductor and you have a step edge with a normal region, then if the orientation of the superconducting order parameter and the step edge are in this particular way, then you can look at this expression and you can very quickly see that there should be a zero bias state inside the superconducting gap. It's a bound state. Whereas if you have a 45-degree step edge, then you should see no zero bias peaks. And if you didn't know that a material was D-wave and you did this experiment, if you saw a zero bias peak for one step edge and no zero bias peak for a 45-degree step edge, you might think that this material might be D-wave, for example. However, for a P-wave superconductor, no matter what the direction of the step edge is, for any direction step edge, you always expect to see Andreev bound states. And more importantly, for a D-wave superconductor, you see an Andreev bound state at zero energy, whereas in a P-wave superconductor, you can solve this equation and find that for all energies inside a superconducting gap, a bound state is allowed. So basically, if you have a step edge, you will have a mode running along the step edge, which exists at all energies inside a superconducting gap. So looking at these Andreev bound states is actually extremely useful. And in fact, it's the same Andreev scattering process that gives rise to all of the edge states that people keep talking about in superconductors. So even these Majorana arcs and Majorana chiral edge modes, the process that gives rise to these edge states are all Andreev processes. So a step edge is a very good place to look for interesting features and to see if you see any resonances that might give you an indication of the order parameter of the sample. So here, for example, is a region without step edges, and here's a region of the sample with step edges. So since we have the ability to move around and look for these regions, we naturally went to the step edge to look at the spectra. So here is a series of spectra taken from, this is a step edge, from far away, coming closer and closer to the step edge. This funny feature is actually the Kondo feature I was showing you earlier. It's just got a funny line shape because the tip had a strange shape, but this is the Kondo effect. What you find is as you get closer to the step edge, you can see that at low energies, you can see a feature developing. So right here, you can see that right at the step edge, you see a feature. In fact, if you zoom in, what you find, so here's another series of spectra. Far away from the step edge, you see the superconducting gap. And right at the step, very close to the step edge, you see this feature that develops. So this feature is really interesting because what we found is that whether this peak appears below the Fermi energy or above the Fermi energy depends on the direction of the normal to the step edge. For example, here is a terrace, it's just a step up and a step down. If you went to this step edge, you would see a peak below the Fermi energy. And if you went to this other step edge, you would see a peak above the Fermi energy. And the interesting thing about these peaks is that these peaks lie inside the superconducting gap. So essentially, you have these in-gap bound states, which have chiral symmetry, meaning they have a handedness. So depending upon the direction, whether it's this direction or this direction, for the step edge, you see a feature which is either below the Fermi energy or above the Fermi energy. So what does this feature have to do with superconductivity? Well, one thing is, like I said, it lives inside the superconducting gap. The second thing is we checked its temperature dependence, and it disappears right around TC. So this is 1.5 Kelvin, right? The feature is gone. So this is a magnetic field dependence. So here's this is a trench actually. So on this side, you have the red spectra, which is, you have a peak on positive sides. On this side, you have the blue spectra, a peak on the negative side. And you can see that both of these things disappear as a function of magnetic field. 10 Tesla is Hc2 for the sample, and right around Hc2, these peaks go away. So the temperature dependence, the magnetic field dependence, and I forgot to say, particle-hole symmetry. So each spectrum by itself is not particle-hole symmetric. I'll come back to that in a few minutes, which is a big problem actually. We have to understand that. However, if you look at the positions of these peaks, they're exactly particle-hole symmetric, meaning that if you, EA minus and EA plus are the same energy, just on opposite sides of the Fermi energy. So what we find is that in this material, there are in-gap states, so states inside the superconducting gap, that are sensitive to some kind of a vector that's associated with superconductivity. So if you have a vector associated with superconductivity, that immediately tells you that, this autoparameter should be either some kind of a P wave or an F wave autoparameter. It doesn't tell you anything about whether it's chiral or helical, but the fact that you have chiral in-gap states, by that I mean states with this handedness that are sensitive to direction. So this direction and this direction are different in your superconductor, tells you that the autoparameter, your superconducting autoparameter, has a vector associated with it. So this is just the beginning actually. So the question is, there's this unusual line shape. So each spectrum by itself doesn't have particle-hole symmetry. And I'll come back to that in a second. The line shape cannot be explained simply by breaking inversion symmetry, because if you broke inversion symmetry, you would still see states at any given point, both above and below the Fermi energy. So inversion symmetry is not enough to explain this line shape. The question is, can the chirality of these edge state modes, by chirality I mean handedness, be explained by the existence of chiral edge states near the step edges? So that is one of the questions we're trying to answer. We believe that this line shape, once we understand this line shape, it'll give us insights into the superconducting order parameter. So let me just say a few more things. The first thing is the question of particle-hole symmetry. So in a superconductor, which is unconventional, like a D wave or a P wave superconductor, you can have potential scattering that can give you bound states inside the superconducting gap. But these states, just because of because they're made up of Bogoliubov quasiparticles, are always particle-hole symmetric in the sense that if you have a peak at minus E, you must have a corresponding peak at plus E. Their heights could be different, but you must have, if you have one, you must have the other. The relative heights could be different. However, in our case, we see a peak at minus, let's say minus 240 millivolts or something. But at the positive account, its positive energy, we see a dip instead. Okay, so this particle-hole asymmetry is really extremely mysterious for a superconductor. So now we're entering the realm of conjecture, right? Let's ask the following question. If we had chiral edge states in our superconductor, let's say this, this superconductor, all indications are that it's triplet. That's not the question. The question is it a chiral P-wave superconductor? So if it were a chiral P-wave superconductor with chiral edge states, could we find a way to obtain the kinds of line shapes that we see? That's the question I'm trying to ask. So the first question is, if you have a chiral superconductor, then in which direction is the chiral axis? So fortunately, we already know quite a bit about this material. We know that from the penetration depth measurements that this system likely has point nodes along the A-axis. And in fact, I think even specific heat measurements indicated that the system has point nodes. So the material has point nodes along the A-axis. And by symmetry, it suggests that the chiral axis is along the A-axis. So A-axis for us is actually in the direction of the tellurium chains that I was showing you earlier. So let's construct a little box of uranium ditelluride. If you have a chiral, if this were a chiral superconductor with nodes along the A-axis, then what you would expect is to have chiral supercurrents running in this direction on the surface of this material. So that's what you would expect. So that means that on the surface of this material, you have this kind of in-gap states with linear dispersion that span the superconducting gap. So if you have the scenario, then can we actually explain our data? So the one way we could think of explaining our data is that when you go close to the step edges, due to the presence of the step edge, certain momenta are blocked or certain momenta are enhanced while others are blocked. And so for example, if you went to this step edge, you would selectively tunnel into these states. And if you go to this step edge, you would selectively tunnel into these states. And that's because you can imagine that the tunneling electrons come in, they try to go this way, and it might be harder than going this way. So if you have this momentum selective tunneling at the step edges, along with the chiral state, then you can explain our line shape. So that's one scenario that we could think of for explaining the line shape that we see. I'll show you more data that, that we still need to explain about these line shapes. But before I do that, let me tell you one thing. So I was talking about having chiral edge modes. One question you can ask is, if this is indeed a chiral superconductor, then do you have evidence for broken time reversal symmetry? And in fact, this is a recent paper. This is on the archive. And what they've done is, this is from Aaron Kapitolnik's group. They've done Kerr effect measurements. And what they find is that they find evidence from polar Kerr effect measurements that there's actually broken time reversal symmetry below TC in the system. Okay, so this is the last thing I want to show you. So in our search for understanding the strange line shapes that we were seeing, we also looked at IV, which is current versus voltage. And we found something quite remarkable. So this is simply current, which is the integrated dI/dV versus bias voltage. And so this, you can just at large energy ranges, you should just see an IV that looks sort of linear, right? But if you zoom into a small energy range, which is the superconducting gap, this is what you see. So the red spectrum is on one step edge and the blue spectrum is on the other. So here's a sort of a background line that I've subtracted from the red and blue spectra. And if you do that, what you find is that on one step edge, you have excess current, so this is positive. And on the other step edge, you have a deficit current, okay? So negative currents. If you can ask the question, what does this IV signal have to do with this strange line shape I was seeing earlier? And in fact, they're the same signal. You can see that quite clearly. So here's dI/dV measured with a lock-in. This is the superconducting gap. This is on one step edge. This is on the other step edge, right? And now here's the IV measured at the same positions. If I take a derivative of our IV, it looks like this. So this feature and this feature in the IV, they are the same thing, okay? So this is just a current map at zero bias means nothing. There's some rounding, but the current map basically disappears above TC. So this whatever this excess current is or deficit current, it only exists in the superconducting phase. Why is this strange? Well, it's strange because I don't want to go into this because we don't have much time left, but let me just tell you, IV should switch sign, meaning the current should switch sign when the voltage switches sign. So if you have positive voltage, you should have positive current. Electrons are going in one direction. When you have negative voltage, electrons go in the opposite direction. So the current sign should switch. What we find instead is no matter what the bias voltage is, sorry about that. No matter what the bias voltage is, we have only one sign of the current, and that sign depends on which step edge you're on. So it's almost like when you go to this step, you have an excess current, and when you go to this step edge, you have a deficit current. So we don't understand the mechanism by which we see this, but it would be certainly consistent with the existence of a chiral edge mode. Okay, so I think that's all I have to say. And finally, the last thing I want to say is that these were step edges parallel to the a-axis. We also found step edges diagonal to the a-axis. They all show in-gap states. However, those in-gap states are symmetric. They exist right at the Fermi energy, and they're symmetric about the Fermi energy. Okay, so this is the summary. So our data, what we see is the existence of sort of a edge states which show a chirality. There are many open questions. There's a question about the superconducting order parameter. There are already a bunch of theoretical works suggesting both unitary and non-unitary order parameters. If it were non-unitary, it would certainly explain the residual specific heat. But then there's another mystery here, which is thermal conductivity seems to indicate that there are no excess carriers at low temperature. So these two have to be reconciled. Is this a chiral state? There's indications from Kerr effect of broken time reversal symmetry. These should be confirmed. There are other materials related questions. For example, is spin orbit coupling important? is the Fermi surface really quasi 2D? Should you treat this as a quasi 2D system, or should you treat this as a 3D system? So I think there are really important questions yet to be answered. But I think, if you see the weight of all the measurements that have been done on this system, I think it's a very interesting and pretty unique superconductor. So that's all I have to say. Thank you for your attention.
Thank you, Vidya. I think everybody, we can also show a clapping sign. This is the virtual world, if you would like to do that. We do have a number of questions, so let's see. Herman.
Yeah, hello, can you hear me? Thank you. Yeah, so I have one question. Why, I would have liked to see also a nice PCS superconducting gap, but I guess we can all figure out how it looks like. Now, my question is more, why do you see vortices, or have you worked on that?
So far, we have not seen any vortices.
And why?
So I don't know. One possibility. So you have to ask. So this is what our spectra look like. So this spectrum is taken with a superconducting tip. This is taken with a normal tip. The fact that we see a doubling of the superconducting gap with a superconducting tip, this was actually a uranium ditelluride tip, suggests that this is a superconducting gap. But you can see it's extremely shallow. So you can ask the question, why is this gap so shallow? One possibility is that this gap is shallow because the gap is filled with surface states that you would expect for a chiral superconductor. And so then one could ask, well, the problem is usually when you see vortices with XTM, your signal to noise comes from the contrast between some kind of vortex bound state and the rest of the superconductor. And one possibility is that because of the presence of these surface states, it's very hard to see the vortices in the system. I personally think we should sort of cool down more to even lower temperatures and turn on the field again and check. So we don't have that capability. Maybe someone else can do it.
Thank you.
Oh, I was muted myself. Another question from Younglang.
Hi, I have a question regarding the superconducting gap. Do you see any response, for example, in gap states near atomic impurities, either magnetic or non-magnetic?
No. So all our in-gap states have been at step edges. So we've seen in-gap states on all the step edges that we've looked at. But nothing dramatic. So again, I would say, we have the shallow gap, so I don't know what's hiding underneath it, but nothing dramatic at impurities.
No QPI, I assume, by that?
Not yet.
Okay, thanks.
We're trying, the thing about QPI is that it's really important what kind of impurities you have, which plane they are in. And so I think once we figure out, we should see QPI. That has nothing to do with superconductivity, right? We should see QPI even in the normal state. That's just a Fermi surface feature. So once we figure out where we need to dope to get QPI, we should be able to see QPI. Yeah.
Okay, thank you. Looking forward to that.
Okay.
Another question by Somesh.
Hi, Vidya, again. So you have one of your slides, you mentioned the type of stepages. So different type of stepages gives you sometimes bound state and sometimes not, depending on your order parameter symmetry.
Oh, yeah.
So did you try on other kinds of stepages and where the bound states look the same?
Right, so that's what, sorry, I went really fast. I wanted to not, keep you guys, but that's what this slide was meant to show. So this slide shows you these kinds of step edges, which are parallel to the a-axis, right? So this is a sort of a mesa. This is a trench, and we see these states below and above the Fermi energy. And then here's a 45-degree step edge, and there you see a bound state exactly at 0.
Oh, okay.
So Vidya, you also basically just see one energy for the bound state in the other direction as well.
In the other direction,
In parallel to A.
Yeah. They're almost identical. So the thing about these line shapes is they're not only, I could take this line shape and basically flip it around and it would look like this. They're identical. They're also identical if I inverted it. So all the areas are exactly the same. Yeah, I don't understand what this is.
Mm-hmm. Okay. Next question by Anton.
Yeah. So I'm wondering, you showed the Fermi surface before, and it was almost it was extremely anisotropic. So the electrons are, by the looks of it, are moving only in a couple of directions. It's a little bit unclear here. Especially in the cross sections, it's in the cross section it seems quite extreme. So how are these directions oriented compared to the step edges?
One of these directions is the direction of the step edge. So A-axis, we have only one axis, which is a crystallographic axis. The other directions are not, meaning, you know, the ABC. So A-axis is, for us, this direction is the A-axis.
Mm-hmm.
Assuming that the Fermi surface, you know, the problem with this Fermi surface is they're plotting kx, ky, kz. I'm just making an assumption here is that kx, ky, one of these is A, the other is B, and the third one is C. Now, if that's not true, then I don't know.
Mm-hmm.
So
the surface is like a diagonal cut through this Fermi surface, right?
Yes, not exactly diagonal, but yes, it's a cut through this Fermi surface. Yes, correct.
What do you mean by not exactly diagonal? It was 1, 1, right?
0, 1, 1, yeah. It's not 1, 1, 1, it's 0, 1, 1.
Yeah, okay, yeah, I see.
Mm-hmm. Yeah.
All right, thanks.
Sure.
All right, so we have another question by Anand.
Hi. Yeah, so my question is also again regarding the gap.
Yes.
So if you think this is a Kondo, then you can also expect that the gap vanishes around say 1K, because looking at the width of the gap, the Kondo temperature might come around 1. So how do you exclude that? Yeah.
But the thing is, there's a Kondo resonance at higher energies, remember? And that Kondo energy scale is pretty large. It's between 30 to 50 Kelvin. From our data, it's like 30 Kelvin. 30 Kelvin, and the superconducting energy, TC, is 1.6 Kelvin. The superconducting gap energy scale is a few hundred microvolts. The Kondo energy scale is a few millivolts. So they're very well separated in energy. So below the Kondo temperature of 30 Kelvin, you can think of this as a metal. A heavy band, but still a metal.
Okay. I was also wondering about your spectra do not show the sharp coherence peaks. So
correct, they don't, and that's what I was trying to explain, that we don't understand why the spectra look the way they do, but the temperature at which these dips disappear and the magnetic field at which they disappear is all consistent with it being due to superconductivity. But you're absolutely right. They don't show sharp coherence peaks.
All right. We have one question from the chat. So I received this in the chat. Says, could you clarify what you meant, and this is by Vala Fatemi, could you clarify what you meant by the excess current? It went a little fast. Okay, it looked like finite absolute current at 0 applied bias, maybe?
Yeah. Okay. Yes. Vala, that's good catch. I don't think that I'm not, okay, I don't want to say anything about this. This thing here, now, two things I want to say about this. One is, this measurement was done with the modulation on. Because when we took this data, we didn't know we were going to see this. So we happened to take IV at the same time as DIDV. And when we take DIDV, our modulation is on. And when our modulation is on, there's an averaging. So imagine that this is like sort of V-shaped, which goes to 0, and you average the modulation, like a little modulation averages that, and that can cause this rounding, right? However, we have done the same measurements without the modulation, and we still see a little bit of rounding, and that is not physically possible. So the only other thing I could think of was maybe it's noise, but there's a problem there too, because it's a very strange noise that pushes this up. Okay, I don't know, but the only thing I can think of is that it's some kind of modulation or noise, and that this in reality actually goes to 0. Good catch, Vala.
Okay, so maybe, do you still have energy for 2 more questions? Yeah, it's been a while. Yes, all right, so next question is by Kenji Yasuda.
Yeah,
go ahead.
I wonder if you can flip the sign of the order color of the parameter by magnetic field.
Yes. So yeah, that's a really good question. So I was looking for you. I can't find you. Okay, that's a really good question. We have only perpendicular fields. And the order parameter, I think, requires an in-plane field to be flipped. And I think it would be fantastic to do that. It would be a really nice experiment. We just we don't have the right field.
So with autoplane, you cannot?
No.
Flip it. Okay,
yeah.
Thank you.
All right, so that may be all of the questions. I don't see any more raised hands. All right, so thank you very much, Vidya, again, for a great talk. So just as a reminder, so we will have our next talk in 2 weeks' time by Nicola Spalding, and that I will share the links again quickly. The registration is open for that one as well. All right, so thank you so much.
Thanks, bye.
Bye.
I saw some familiar faces. Nice to see you all, and nice to see even the unfamiliar faces.
Thank you.
Bye.